Alright, so this is going to be your last section of Unit 4, and it's all about phase changes. Since we've talked about all the different states of matter, now we're going to talk about moving between those states. So our example for this entire presentation is going to be water, because you're familiar with all the phases of water, you've observed all of the changes between those phases. So as we go through here, water is going to be my primary example that I use to describe all this stuff. So the first phase changes that we're going to talk about are the ones that require energy. And as you can see from my little graphic in the right-hand corner, there are 6 different phase changes that we need to discuss. And one of the first one that requires energy is melting. So it's important to know that heat will flow from hot to cold. So when ice melts, that energy is absorbed in the ice is not used to actually raise the temperature of the ice, because during the process of any phase change, the actual temperature stays the same. All that it does is that energy disrupts those hydrogen bonds holding the water molecules together in the ice crystal itself. And so when those molecules on the surface of the ice absorb enough energy to break those hydrogen bonds, those molecules are then able to move apart and thus enter the liquid phase. And so as those molecules start being removed, the ice cube starts to shrink and you see the melting. The amount of energy that it takes to melt 1 mole of a solid depends on the strength of the forces keeping the particles together. So as you can imagine, hydrogen bonds are our strongest intermolecular force, so it requires a relatively large amount of energy to melt water. So melting point is defined as the temperature at which the forces holding its crystal lattice together are broken, and it thus becomes a liquid. Our second phase change that requires energy is vaporization. And while ice is in the process of melting, the temperature of the ice-water mixture remains constant, as I said before. During a phase change, the temperature stays the same. Now, once all of the ice has melted, additional energy is added to the system that causes your increase of kinetic energy that actually increases the temperature. Now, what you want to remember is that a vapor is something that is not a gas at room temperature. That's why water vapor is called a vapor, because water is a liquid at room temperature. So, vaporization is the process where a liquid changes to a gas or vapor. And then if your input of energy is gradual, the molecules in a liquid tend to escape from the surface of the liquid, because there are less attractive forces there. There are only attractive forces on the bottom side of those molecules, rather than the molecules in the middle that have attractive forces surrounding them on all sides. So if that happens, the molecules towards the surface start to escape. That leads to evaporation, which only occurs at the surface of a liquid. And evaporation can happen at virtually any temperature, because at any time, some molecules will always have enough energy to evaporate. And evaporation is the method by which your body controls its internal temperature. And since we're talking about vaporization, of course, vapor pressure comes into play, which is the pressure exerted by a vapor over a liquid. And then boiling point, or the point at which vaporization occurs, is the temperature where the vapor pressure of a liquid equals the atmospheric pressure. And we've talked about that before. At the boiling point, molecules throughout the liquid have enough energy to vaporize, and so the bubbles will collect below the surface and rise. And then I've also put an example of vapor pressure here. You can see an open container and a closed container containing water. And you can see those molecules escaping the surface of the liquid in the open container, and they are able to escape out into the atmosphere. Versus the closed container, when they do evaporate, they start to collect above the actual liquid, causing the vapor pressure to be higher in the closed container than it is in the open one. Another phase change that requires energy is sublimation, which is where a solid changes directly to a gas without first becoming a liquid. Carbon dioxide is obviously able to do this. That's dry ice, which is my picture that I have right here. Iodine is able to do it, and believe it or not, water is actually capable of doing it and does it in your freezer quite often. That's why ice cubes shrink over time. So we talked about the 3 phase changes that require energy, and now we're going to start talking about the ones that release energy. Condensation is our first one, and so you have to think about when water vapor starts losing energy, it's becoming more slow moving, and so when it's slower, that means it's more likely to interact with another molecule and form a hydrogen bond. And when those hydrogen bonds are formed, it signals that change from the vapor phase to the liquid phase because it's kind of locking those particles closer together. So condensation is the reverse of vaporization, or the process where a gas or vapor becomes a liquid. And when hydrogen bonds form in liquid water, energy is always released. Bond formation releases energy. Deposition is where a substance changes from a gas or vapor directly to a solid. Water is able to do this as well. Freeze drying is where that's used. And then, of course, freezing, the opposite of melting. So you have to picture, as heat is removed from water, the kinetic energy is going to decrease. So your molecules are moving far more slowly, which means they are less likely to flow past one another. And then when enough energy has been removed, those hydrogen bonds between the water molecules keep those molecules frozen into set positions. And that is where your freezing point occurs, the temperature where a liquid is converted into a crystalline solid. And the last part of this section is all about phase diagrams. And there's a lot of information that you can get from a phase diagram. And I actually have used these quite a bit, and you need to know and be able to read them. And so there are 2 variables that combine to control the phase of a substance: the temperature of the substance and the pressure at which the substance is held. And they can have opposing effects on something. For instance, if I increase the temperature of something, that's going to try to increase the vaporization of that substance. However, if I were to increase the pressure on that same substance that I had increased the temperature of, I could prevent that vaporization from occurring because I can increase the vapor pressure. So, a phase diagram is a graph of pressure versus temperature that shows where a substance exists under different conditions of temperature and pressure. So it's going to show you which phase a substance exists in given a certain temperature and a different pressure. So I'll show you one, the one for water. So this is what water's phase diagram looks like. So it'll show you the different phases where the water is existing, and it has temperature at the bottom and then pressure on the side, and this pressure is in atmospheres, which this is the phase diagram that I like to use because we use atmospheres a lot. So, and then it has a little key at the bottom here. It's got its normal freezing point labeled right here for water. The normal boiling point is right here at 100 degrees Celsius, and you'll see that the normal freezing point is at 0. And then your triple point is marked right here, and then it has another point marked, which is the critical point. So all of these are very important locations on a phase diagram, so we'll talk about them a little bit. So here's your phase diagram again, and at points that fall along the curves of the graph, 2 phases of water can coexist. So you can have liquid and gas existing at the same time at your boiling point. You can have ice and liquid water existing at the same time at your freezing point. Now, the triple point that I discussed earlier, which is the green dot on your graph, is the point where the temperature and pressure are at the point where the 3 phases of that substance can coexist. So solid, liquid, and vapor phases of water all exist at that triple point there at 0.01 degrees Celsius and 0.006 atmospheres. You have all of them coexisting at the same time, which means all 6 changes can occur at that temperature and pressure. The critical point, which is the yellow dot on the graph, is the critical pressure and critical temperature above which water can't exist as a liquid. So if water vapor is at the critical temperature, an increase in pressure will not change the vapor into a liquid. All right, that is going to conclude the section 4 notes, and we will come back and talk about these next time and go through some of these diagrams together.